Welcome to Crashcast Java, where we dive deep into the world of Java programming. I'm Victor, and today we're joined by Sheila to explore synchronization mechanisms in Java. Sheila, why don't you kick us off by explaining what synchronization is all about?
Absolutely, Victor. Synchronization in Java is all about managing how multiple threads access shared resources. Imagine a busy kitchen with multiple chefs trying to use the same utensils and ingredients. Without proper coordination, chaos ensues. That's where synchronization comes in. It ensures our program's threads play nice together.
Great analogy, Sheila. So why is synchronization so crucial in Java programming?
Well, Victor, as programs become more complex and leverage multi-core processors, we often have multiple threads running simultaneously. These threads might need to access or modify the same data. Without synchronization, we can end up with what we call race conditions, where the outcome depends on the timing of thread execution. This can lead to unpredictable results and bugs that are notoriously hard to track down.
I see. So how does Java help us tackle this challenge?
Java provides several mechanisms for synchronization. The most basic one is the synchronized keyword. When you declare a method or a block of code as synchronized, Java ensures that only one thread can execute that code at a time. It's like putting a lock on the kitchen door. Only one chef can enter at a time.
That makes sense. Can you give us a real-world example where this might be important?
Certainly. Think about a banking application. If two people try to withdraw money from the same account simultaneously, we need to ensure the balance is updated correctly. Without synchronization, we might end up with an incorrect balance or even allow overdrafts that shouldn't happen.
I can see how that could be a major problem. Are there any other synchronization mechanisms in Java?
Yes, Java also provides more fine-grained control through the use of locks. The lock interface and its implementations like re-entrant lock allow for more flexible locking strategies. There's also the volatile keyword, which ensures that variable updates are always visible to other threads.
That sounds a bit more advanced. Could you elaborate on the volatile keyword?
Sure, Victor. The volatile keyword is used for variables that might be accessed by multiple threads. It guarantees that any thread reading the variable will see the most recently written value. It's particularly useful for flag variables that might signal other threads to stop or change behavior.
Interesting. Are there any common pitfalls developers should be aware of when working with synchronization?
Absolutely. One major pitfall is deadlock, where two or more threads are waiting for each other to release resources, resulting in a standoff. Another is over-synchronization, which can hurt performance. It's important to synchronize only what's necessary and to always release locks properly.
Those sound like tricky issues to handle. What are some best practices to avoid these problems?
Good question. Some best practices include using higher-level concurrency utilities like thread pool executor or Java, util.concurrent collections when possible. These are designed to handle many common synchronization scenarios. Also, keeping synchronized blocks as small as possible helps minimize contention between threads.
That's really helpful, Sheila. As we wrap up, could you touch on how synchronization in Java has evolved over time?
Certainly. Java's synchronization mechanisms have come a long way since its early days. The introduction of the Java util.concurrent package in Java 5 was a game-changer, providing high-level concurrency utilities. More recently, Java has introduced even more powerful constructs like the fork-join framework and completable future for managing complex asynchronous operations.
Fascinating stuff. Before we go, let's quickly recap the key points we've covered today.
Sure thing. We've discussed the importance of synchronization in multi-threaded Java applications, explored basic mechanisms like the synchronized keyword and locks, touched on advanced concepts like the volatile keyword, and highlighted some common pitfalls and best practices. We've also seen how synchronization in Java has evolved to meet the demands of modern concurrent programming.
Excellent summary, Sheila. For our listeners who want to dive deeper, here are 3 advanced topics to explore: the Java memory model, non-blocking algorithms, and the disruptor framework for high-performance inter-thread messaging.
Great suggestions, Victor. Those topics will definitely give our listeners a deeper understanding of concurrency in Java.
Thanks for joining us today, Sheila. And thank you, listeners, for tuning in to Crashcast Java. If you enjoyed this episode on synchronization mechanisms in Java, be sure to subscribe for more deep dives into the world of Java programming. Until next time, happy coding!